Hello everybody, this is V.R. Seshagiri Rao, Associate Professor in Electronics and Communication Engineering Department. So today I am going to discuss about the different current and voltage characteristics of MOSFET in saturation and non-saturation regions. And also I am going to discuss about the threshold voltage concept in MOSFETs. Now these are P MOSFET and N MOSFET. You know, the P MOSFET is formed on N substrate and N MOSFET is formed on P substrate. So this is the N MOSFET and this is the P MOSFET. And these MOSFETs are of enhancement type and there is no channel implant. And there are three terminals in a MOSFET: source, gate and drain. And for a N MOSFET, if you apply a positive voltage to the gate, then a channel is formed and the MOSFET is said to be on. Similarly, for a P MOSFET, a negative voltage is applied to the gate, then the P MOSFET is turned on. So these are the transistor symbols and switch level models. And N MOSFET, just now I told that if you apply a positive voltage to the gate, then the MOSFET is on, and you can imagine that the switch is closed. So you can imagine the MOSFET like a switch. If you apply a positive voltage to the gate of N MOSFET, it develops the channel or it induces the channel and the MOSFET is turned on. So the switch is closed. Similarly, if zero voltage is applied to the gate, then the MOSFET is not turned on and you can represent it as an open switch as shown here. Now coming to the P MOSFET, if zero voltage is applied to the gate, then the P MOSFET is turned on and you can model it with a closed switch. Similarly, if 1 is applied to the gate of a P MOSFET, then it is in off condition, or you can imagine that the switch is in open condition. Okay. Now let us come to the IDS versus VDS relationships in different regions. So the whole concept of MOS transistor, it evolves from the use of a voltage on the gate which induces a charge in the channel between source and drain. And this charge can be made to move from source to the drain under the influence of electric field due to the application of VDS. So if VDS is applied between drain and source, then this induced charge, it moves from source to the drain. Okay. So whenever there is a movement of charge, it is nothing but a current. So this current between drain and source, it not only depends upon the gate to source voltage, but also it depends upon the electric field between drain and source. Now this is the N MOS transistor structure, and this is the source terminal, and this is the drain terminal, and this is the gate terminal, and the distance between source and drain is called the length of the channel L. Okay, and L is related to lambda this way. L is equal to 2 lambda, and this lambda is not the lambda what we study in optics. This is different. So lambda is related to the length of the channel by the equation L is equal to 2 lambda. And this is the width of the channel W. The width of the channel is W. And the gate is made of the polysilicon, and source and drain, depending upon the type of MOSFET, it depends. For N MOSFET, the source is N plus, the drain also is N plus. For P MOSFET, the source is P plus and the drain is P plus. Now let us see how to derive the equation for IDS. Okay. Now what is IDS? We can say IDS is nothing but the current between drain and source, and IDS is equal to, you can say, the flow of charge carriers is from source to the drain. So IDS is equal to minus ISD. Minus ISD. So what is this is equal to what? This is equal to charge developed by the transit time. So that is nothing but QC divided by the tau. Tau SD is the transit time. So this is equation 1. Okay. Now what is the transit time? Transit time is for the time taken by the charge carriers to travel from source to the drain. Okay. So transit time, you can say, transit time is equal to tau SD, and that is equal to L by V. What is L? L is the length of the channel and V is the velocity of charge carriers. And velocity of the charge carriers depends upon what? It depends upon the electric field, and also it depends upon the mobility of the charge carrier. There are two types of charge carriers, as you know, electrons and holes. So these electrons and holes, they have their own mobilities, and the mobility of electron is 2.5 times more than the mobility of hole. So the velocity V, it depends upon the mobility of the charge carrier, and also it depends upon the electric field strength. So we can write V, which is the velocity, that is equal to mu EDS. EDS is the electric field between drain and source. So what is EDS? EDS is nothing but VDS by L. Always the electric field is nothing but the voltage by the distance. So we can say mu EDS is nothing but mu VDS by L. Okay. Now tau SD is nothing but L by V, right? So we can say that tau SD which is nothing but L by V. So L by V, that means L into L divided by mu V ds. So this is equal to L square by mu VDS. So this is say equation 2. Okay. Now, what is mu? Mu is the mobility of the charge carrier, and the mobility of the charge carrier, just now I have told you that the mobility of electron is 2.5 times more than the mobility of hole. And the mobility of charge carriers, it depends upon the distance from the center. Suppose if you take this as the bulk, then in the bulk the mobility will be less, but on the surface you are likely to have more mobility because there are no obstructions, there are no atomic collisions. So the typical values of mu mobilities at the surface are mu n is equal to 650 cm square divided by volt second. That is for the electron. And for hole, mu p is equal to 240 divided by v second cm square. So these are the typical values of mobility. Okay. Now, the MOSFET has two regions of operation, saturation region and the non-saturation region. You have already studied the MOSFET characteristics, VI characteristics in EDC. So the MOSFET characteristics are typically like this. These are the MOSFET characteristics. On the x-axis, we have VDS. On y-axis we have the IDS. So here this is the non-saturation region and this is the saturation region. Non-saturation region is also called as the ohmic region, or you can also call it as triode region. And here the values of VDS are lesser. So you can see very clearly that for the small values of VDS, the MOSFET is in the non-saturation region, and here it is in the saturation region. In saturation region, the MOSFET current is almost same, constant, so it acts like a constant current source. Now first let us derive the equations for the non-saturation region. So non-saturation, just now we have discussed that for small values of VDS, the MOSFET operates in the non-saturation region. Small values means how much? So it is like this: for VDS less than VGS minus VT, the MOSFET operates in the saturation region. Okay. So when you apply a voltage to the gate, it induces charge carriers in the channel and the channel inversion it takes place. So what is the effective gate voltage? For small values of gate voltage, the MOSFET is not turned on. So you have to apply a certain minimum voltage so that the MOSFET is turned on. So the minimum voltage to turn on the N MOSFET is called as the threshold voltage. Also we can say the minimum voltage to form the channel in enhancement N MOSFET is called as the threshold voltage. So what is the effective gate voltage? So effective gate voltage is nothing but, so VGS is equal to the effective gate voltage VG is equal to VGS minus VT. So this is the case where no voltage is applied between the drain and source. So when you apply a voltage between drain and source, there is going to be ohmic drop from drain to the source. So at the drain terminal, you are going to have maximum voltage. At the source terminal, you are going to have zero voltage. So what is the average voltage? The average voltage is, the maximum voltage is VDS. The average voltage is VDS by 2. So what is the effective gate voltage? Effective gate voltage is going to become VGS minus VT minus VDS by 2. This is the effective gate voltage. Okay. So now the charge developed in the channel, let us first calculate. The charge developed in the channel is given by this formula Q naught. Q naught is the unit charge developed in the channel, which is equal to Eg epsilon INS into epsilon naught. Okay. What is epsilon INS? Epsilon INS is the relative permittivity of the silicon dioxide, and epsilon naught is the permittivity of the free space. Okay. Now let us, this is a unit charge. So what is the total charge? You have to multiply it by the area. And what is the area? Area is nothing but, what is the area? See, here you have W and here you have L. So what is the area? Area is equal to WL. So you have to multiply this by the area to find out the total charge. So I can write QC equal to Eg epsilon INS and epsilon naught into A. So that is equal to Eg epsilon INS into epsilon naught A. Just now I told you that A is equal to WIL. Okay. So what is Eg? Eg is the electric field, the effective electric field. For that, you have to take the effective gate voltage and then you have to divide it by the distance. So we can say QC is equal to WL, okay, epsilon INS, which is the relative permittivity of silicon dioxide, which is approximately 4, and epsilon naught divided by D, because electric field is you have for electric field you have to take this voltage, effective gate voltage, and then divide it by the distance. So I will take this voltage, I'm going to take this voltage, and I'm going to divide it by the D distance. So this is equal to VGS minus VT into VDS by 2. So this is the charge. So this is the equation 3. Okay. Now let us move further. Now let us use the equations 2 and 3 and 1. Okay. So using 2 and 3 in 1. So what is 2 and 3? So this is 2. What you have seen here, this is 2 and this is 3, and you use it in 1 to find out the value of IDS. So then you get IDS equal to epsilon INS epsilon naught mu is the mobility, and divided by D, and W by L, and VGS minus VT minus VDS by 2 and multiplied by VDS. Okay, so this is IDS. So I can write this equation like this. I will move this VDS inside here. Okay. And I will replace epsilon INS epsilon naught mu by D as K. Then this equation becomes K W by L. What is K? K is nothing but epsilon INS epsilon naught mu divided by D. So KW by L into VGS minus VT into VDS minus VDS square divided by 2. So this is equation 4. So where K is equal to epsilon INS epsilon naught mu divided by D. Okay. Now I will represent in a different way by using parameter beta, where beta is equal to K W by L. Then equation 4 becomes IDS is equal to beta VGS minus VT into VDS minus VDS square divided by 2. Okay, so let me call this as equation 4A. Okay. See, in MOSFET we have gate capacitance. Where this gate capacitance is coming? Because I have a gate which is made by a polysilicon. This is a polysilicon gate, and this is the bulk P substrate. So these two are separated by a thin oxide of thickness D. This is a thin oxide. So whenever two conductive materials are separated by a dielectric, you are going to have a capacitance. So what is the formula for capacitance? Capacitance is equal to epsilon A by D. And what is A? A is WL and D is the thin oxide thickness. So I am going to convert the IDS versus VDS relationships using the gate capacitance and also using unit area gate capacitance in this way. So the gate capacitance, the CG, is equal to, it is nothing but epsilon A by D. So which is equal to epsilon, epsilon is epsilon INS and epsilon naught. A is WL divided by D. So this is a gate capacitance. And what is K? K, we have defined K as like this. K we have defined as epsilon INS, epsilon naught mu by D, right? So we know that K is equal to epsilon INS, epsilon naught mu by D. So using gate capacitance formula, I can write K as, we can write K this way. K is equal to CG mu by WL. Just we have already derived the relationship between IDS and VDS using K here. So now in here K, in place of K, if you write CG mu by WL, then we are going to get the relationships using CG. So let us do that. So we get IDS is equal to CG mu by L square. Okay. And this is VGS minus VT into VDS minus VDS square divided by 2. So we'll get the relation like this. So let me call this as 4B. Okay. Now I'm going to write the same equation using unit area gate capacitance. What is unit area gate capacitance? It is a capacitance per unit area. CG is the total capacitance and unit area gate capacitance is CG by A. C naught is equal to CG by A. So this is going to become epsilon INS epsilon naught divided by D. So using this relationship is going to become like this. IDS is equal to C naught mu, C naught mu into W by L into VGS minus VT into VDS minus VDS square by 2. So this is the relation 4C. So these are all the relationships we have derived for the non-saturation region. And for saturation region, we have higher values of VDS. So I am going to write the equations for the saturation region. So saturation region begins when VDS is equal to VGS minus VT. So saturation region begins when VDS is equal to VGS minus VT. So in the above equations, if I write VGS minus VT in place of VDS, then I'm going to get the derivations for the saturation region. So the equations are like this for the saturation region. So what you have to do? You have to substitute VGS minus VT for VDS. Again, because saturation region begins when VDS is more than VGS minus VT. So you substitute wherever VDS is there in the above equations, you substitute VGS minus VT, then you get the relationships for the saturation region. So you get IDS is equal to, for the saturation region, IDS is equal to K W by L into VGS minus VT whole square divided by 2. So this is using K. So let me call this equation as 5. Now using beta, where beta is equal to KW by L, so IDS is equal to beta into VGS minus VT whole square divided by 2. So this is using beta. So this is the equation. Okay, let me call this 5A. Now using gate capacitance, so the equation becomes IDS is equal to CG mu by 2L square into VGS minus VT whole square. So this is 5B. And using the unit area gate capacitance, the relationship becomes like this: IDS is equal to C naught mu W by 2L into VGS minus VT whole square. So this is the relationship for the saturation region. Now let us discuss about the threshold voltage concept and its dependence on the substrate bias. So what is the threshold voltage? Threshold voltage is the minimum voltage to form the channel in the case of enhancement MOSFET, and for depletion MOSFET it is the voltage which is required to nullify the channel or to remove the channel. That is a minimum voltage which is to be applied to the gate to remove the channel is called as the threshold voltage for the depletion MOSFET. For an enhancement MOSFET, threshold voltage is defined as the minimum voltage which is to be applied at the gate to form the channel. For a depletion MOSFET, the minimum voltage which is to be applied to the gate to remove the channel. So the threshold voltage, it is expressed as Vt is equal to phi ms Qb minus Qss by C naught into 2 phi Fn, where Qb is the charge per unit area in the depletion layer beneath the oxide, and Qss is the charge density at SiO2 interface. So if this is the MOSFET, this is the thin oxide and this is the polysilicon gate. And Qb is the charge per unit area in the depletion layer beneath the oxide. So it is here. And Ss is the charge density at SiO2 surface. That is, it is here. And C0 is the capacitance per unit gate area, and phi ms is a work function difference between gate and silicon. And phi Fn is the Fermi level potential between the inverted surface and the bulk silicon. So for polysilicon gate and silicon substrate, the value of phi ms is negligible, but the magnitude and sign of Vt, it is determined by the balance between the remaining terms. That is Q minus QSS by C0 and other terms. And so to evaluate Vt, each term is calculated in this way. Qb is equal to 2 into epsilon naught epsilon Si Qn into 2 phi Fn plus Vsb coulombs per meter square. This is a charge density. And Qfn is equal to Kt by Q into L natural logarithm of N by Ni. And QSS is equal to 1.528 depending upon the material into 10 to the power minus 8 coulombs per meter square. So what is VSB? VSB is the substrate bias voltage and N is the impurity concentration in the substrate, and epsilon Si, it is the relative permittivity of silicon, which is 11.7, and for Ni is the intrinsic electron concentration, and that is 1.6 into 10 to the power 10 cm cube at 300 degrees Kelvin, and K is the Boltzmann's constant, which is 1.4 into 10 to the power minus 23 joules per degree Kelvin. Okay, so the body effects are also to be taken into account because the substrate may be biased with respect to the source. So this is what, if the substrate is applied with a voltage, then it is going to change the threshold voltage. And the threshold voltage, it depends upon the substrate bias. And for this MOSFET, N MOSFET, if you increase VSB, it is going to increase the threshold voltage. So the change in threshold voltage, it is given by gamma into VSB to the power 1 by 2, where gamma is a constant and depends upon the substrate doping, so that the more lightly doped the substrate, the smaller is the effect. So the change in the threshold voltage, it depends upon the doping as well as the substrate bias. If in case of light doping, the changes in the threshold voltage are negligible, but in that case, it depends upon the VSB voltage. So you see here, if you increase the value of VSB, okay, if you increase the value of VSB, it increases the threshold voltage. Now, let me give some quantitative figures. When VSB is equal to 0, when VSB is equal to 0 volts, Vt is equal to 0.2 VDD. So if you don't apply any substrate bias, then the threshold voltage is equal to 0.2 VDD. So you can say it is equal to plus 1 volt for VDD equal to 5 volts. So if you apply 5 volts, then the threshold voltage is going to be 1 volt, because 0.2 into 5. So that is 0.2 into 5. So you get plus 1 volt. That is the threshold voltage. And suppose if you apply a substrate bias of 5 volts. So we have discussed that it is going to increase the threshold voltage. In that case, Vt is equal to 0.3 VDD, and that is going to become plus 1.5 volts for VDD equal to 5 volts. Okay. So this is for NMOS. And for PMOS, the trend is same except for negative values of the threshold voltage. Now for NMOS, this is for the enhancement MOSFET. Enhancement MOSFET N type. Okay. Now, what are the values for depletion MOSFET? For depletion MOSFET, it's like this. For a depletion MOSFET, we assume that VSB, when VSB is equal to 0, VT is going to be minus 0.7 VDD. So when VDD is equal to 5 volts, then VT is equal to minus 3.5 volts. Okay, and if VSB is equal to 5 volts, then VTD is equal to minus 0.6 VDD. In that case, you get minus 3 volts for and at VDD equal to 5 volts. So for depletion MOSFET, the threshold voltage is negative. So this is the effect of the threshold voltage with respect to the substrate bias. So with this, I conclude today's session of IDS versus VDS relationships and the threshold voltage concepts. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.